Okay, so we'll try this again. This is my second go at doing question 3. The camera broke. Okay, question 3 then. So question 3 is about understanding about group 1 of the periodic table. You're expected to know and remember what the reactions of lithium and sodium and potassium are like in some detail. You're meant to remember all those details, the fact that they float and they fizz and they disappear, and that they get more vigorous as they go down, and sodium, for example, melts and potassium catches fire to give a lilac flame, or in fact it's the hydrogen that's given off that catches fire and gives a lilac flame. You're asked sometimes though to predict what would happen for the other elements that are lower down the group, and you can predict because you know that the elements get more reactive as you go down group 1, that they'll do the same sort of things but more vigorously. You can't just say for the mark they react more vigorously, but that's understandable. You've got to be clear in what they might do more vigorously. So they would bubble more vigorously, catch fire more quickly, or have a bigger flame, or explode, or disappear, or melt more quickly. One of those things you couldn't just say reacted more quickly, because it's not saying what the observation is. Okay. What you should be able to do quite comfortably, really, and this is well practiced, I would say, by some of you, is that rubidium is more reactive than potassium. And explain, first of all, the way that I would start it, though it doesn't specifically get a mark here, is I would always start this by saying rubidium and potassium both react by losing 1 electron. I think that just structures the answer really nicely, although it doesn't in this particular mark scheme get a mark. But why does rubidium lose its outer single electron more quickly or more easily than potassium's? Well, you have to say that rubidium has more shells, or if you like, just simply larger is okay for that first mark. So more shells, more electron shells. 1 or 2 of you wrote it has more outer shells, but of course everything's only got 1 outer shell. It's the number of shells in total that it has. Rubidium has more shells, or it's bigger, and so there's a less electrostatic attraction. There's my nucleus, and there's my electron in the outer shell that's negatively charged. The further away they are from each other, the weaker the attraction, and so that's the second mark. So less electrostatic attraction. And those of you who are into physics would know perhaps that Coulomb related the force, or the electrostatic force of attraction, as being proportional to 1 over the distance squared. And so if you're twice as far away, the attractive force will be 4 times less. Okay, so 1 over, it's an inverse square relationship. Anyway, that's an aside there. You had to talk the electrostatic attraction being weaker, nothing vague. You could have also mentioned, this is also the second mark, so if you didn't get an extra mark for saying it, you could have also said there's more inner shells for rubidium, and so there's more shielding between rubidium's outer electron and the nucleus, and that would have got that second mark instead of just saying it was further away. The third mark is simply to say that the electron is lost more easily. Okay, so electron lost more easily because of that weaker electrostatic attraction, and that's it for 3 marks. Okay, that's all you've got to do. It's lost more easily. That'll do. That's all of it. Over here, this was done pretty badly on the whole. I think not enough of you know. This came up, by the way, as something that the examiners of last year's GCSEs noted, that not enough people know what it is that makes things alkali. And these are alkali metals because they form a hydroxide, and you're expected to know at your level that a hydroxide is OH minus. And the hydroxide that forms when rubidium reacts with water is rubidium hydroxide. I'm sorry I didn't give you very much space there, but rubidium hydroxide has the formula RbOH. I'm sorry, that's really small. That's the formula of rubidium oxide because rubidium is a 1 plus ion and hydroxide's a 1 minus ion, and so they have 1 of each to make an ionic compound, and it's the hydroxide bit of it that makes the solution alkaline. that makes the water, if it's got universal indicator in it, turn purple. And by the way, there's that. No, that's a different paper. I'm thinking of a different question. The other thing that you should know really that's given off is a gas, and that gas is the gas that catches fire. So it's a flammable gas, and that flammable gas is hydrogen. So you've got 1 mark for getting H2. You got 1 mark for getting rubidium hydroxide, and you get 3 marks if you balanced it correctly. So you did a 2 there, a 2 there, and a 2 there, and that's nicely balanced. I'm not going to spend time teaching you how to balance equations on this video, but do ask if you're not sure. Question D is a bit of a trick one, I suppose. It's easy to be caught out. I wouldn't say it's a trick question. Lots of people put the first box as being the right answer, which is the correct statement about noble gases. Many of you thought that they all have 8 electrons in the outer shell. But if you think about it, helium's a noble gas, and it only has 2 electrons in its outer shell. Remember that helium's got 2 protons, 2 neutrons, and 2 electrons, and has 2 electrons therefore in its outer shell. So it couldn't be that. But you should know that as the atoms get bigger down the periodic table, the boiling points get slightly bigger, and that's to do with the fact those intermolecular forces get bigger as you go down, okay? Because the atoms get bigger. Noble gases, by the way, don't form molecules because they don't react with anything, so it couldn't be that, and they don't form ionic compounds, so they don't react with anything. The calculation, you're going to be moving on to the calculation topic before too long if you haven't already started, which will remind you of how you do relative atomic mass calculations. Relative atomic mass, by the way, is the average mass of all of the isotopes in a compound, bearing in mind they have different abundances. It's a weighted average relative to 1/12 of a carbon-12 atom. Okay, so to do the calculation, though, is relatively simple, which is that you have to do the mass number of the first isotope times its abundance, which is 90.48. You add that, just like you would for any weighted mean calculation, to the mass of the second isotope times its abundance, its percentage abundance, and the same for the third one. You divide that by 100, and that comes to 20.1877. But you've got to look out for the fact that it wants 3 significant figures. If it asks you or tells you to do something to 3 significant figures, you're going to get a mark for that. You're going to get a mark for rounding it. And so you've got to round it to 20.2 for 3 marks there. Let's stop at that point.